For thousands of years, humans looked up at the wandering red dot in the night sky with a mixture of reverence, superstition, and curiosity. Ancient astronomers tracked its peculiar retrograde loops across the constellations, while early science fiction envisioned alien civilizations canalizing its rust-covered deserts. Yet, for all our technological leaps across the 20th century, interplanetary travel remained firmly locked within the realm of dreams. Landing 12 astronauts on the Moon during the Apollo program was an undeniable triumph of human ingenuity. But the Moon is an astronomical backyard, barely 3 days and 384,000 kilometers away. Mars is an entirely different beast. At its closest approach, it lies 55 million kilometers from Earth, and at its farthest, over 400 million kilometers away across the hostile black void of the solar system. To cross that gulf with human beings, keep them alive for years, and return them safely to Earth requires solving the most brutal physics equation in the universe. For decades, space agencies proposed mission architectures centered on massive, multi-billion-dollar expendable rockets. These traditional mission concepts envisioned tiny crews cramped inside capsule habitats, jettisoning empty stages and titanium fuel tanks along every leg of the journey, ultimately expending astronomical fortunes just to plant a single flag and collect a few kilograms of red dirt. That approach treated interplanetary flight as an ultra-expensive one-off expedition. SpaceX and its founder, Elon Musk, took an entirely different philosophical gamble. If humanity is ever to build a permanent, self-sustaining civilization on another world, space travel cannot rely on disposable vehicles. It must be built on rapid, complete reusability, massive payload capacity, and the chemistry of manufacturing rocket fuel directly on the surface of Mars. The vehicle designed to turn that audacious vision into reality is Starship. To understand how Starship can transport hundreds of tons of cargo and dozens of humans to the Red Planet, one must first confront the foundational obstacle of all spaceflight, known to aerospace engineers as the tyranny of the rocket equation. Formulated by Russian mathematician Konstantin Tsiolkovsky in 1903 AD, the equation dictates that to accelerate a rocket, you must burn propellant, but that propellant has mass, which requires even more propellant to lift, which in turn adds more mass, leading to an exponential spiral of required fuel. For a conventional chemical rocket launching from Earth's deep gravity well, roughly 90% or more of its total liftoff mass must consist solely of propellant, leaving only a tiny fraction of 2 to 4% for the actual structure and payload. If you attempt to launch a fully loaded spacecraft from Earth with enough fuel on board to escape Earth's gravity, cruise through deep space, decelerate into Martian orbit, land on the Martian surface, take off again, and fly back home, the required launch mass becomes astronomically impossible. No single rocket ever conceived could lift such a monstrous load off the ground. Starship shatters this limitation by dividing the journey into a modular, reusable architecture built around orbital mechanics, in-space refueling, and local resource utilization. Standing approximately 121 meters tall and 9 meters in diameter, the complete Starship launch system is the largest, most powerful flying machine ever constructed in human history. It generates more than double the liftoff thrust of the historic Saturn V rocket and easily eclipses every other heavy-lift booster ever built. The system consists of 2 distinct stages: the first stage booster, named Super Heavy, and the upper stage spacecraft, known simply as Starship. Both stages are constructed primarily from a specialized cold-rolled austenitic stainless steel alloy known as 304L, rather than the expensive carbon fiber composites or aerospace-grade aluminum-lithium alloys traditionally favored by rocket designers. The decision to build an interplanetary spacecraft out of stainless steel initially baffled the aerospace industry, but it represents a masterclass in thermal and structural engineering. Carbon fiber is notoriously expensive, difficult to manufacture rapidly at scale, and degrades rapidly under the intense cryogenic temperatures of liquefied gases or the blistering friction of atmospheric re-entry. Aluminum loses its structural integrity at relatively modest temperatures of around 150 degrees Celsius. Stainless steel, by contrast, becomes significantly stronger and tougher at cryogenic temperatures of minus 190 degrees Celsius, while simultaneously retaining its structural strength up to temperatures exceeding 800 degrees Celsius. Furthermore, steel costs only a tiny fraction of the price of composite materials and can be welded and repaired outdoors in standard manufacturing hangars. This material choice enables rapid prototyping, mass production of dozens of hulls, and the rugged survivability needed for harsh Martian operations. At the beating heart of Starship is its propulsion system, the Raptor engine. Rocket engines generally operate on complex thermodynamic cycles that burn fuel and oxidizer to spin turbopumps, which force propellants into the combustion chamber at extreme pressures. For decades, the most advanced engines used open gas generator cycles or closed staged combustion cycles that dumped some unburnt propellant or ran oxidizer-rich gas through pumps. Raptor operates on the absolute holy grail of rocket propulsion, the full-flow staged combustion cycle. In this design, all the fuel and a small amount of oxygen pass through one pre-burner to drive the fuel turbo pump, while all the oxygen and a small amount of fuel pass through a separate pre-burner to drive the oxygen turbo pump. This means 100% of the propellants enter the main combustion chamber as fully vaporized hot gases at pressures exceeding 350 atmospheres. Because the gases are already in a gaseous state before entering the chamber, the combustion is instantaneous, hyper-efficient, and capable of generating unprecedented levels of thrust within a remarkably compact envelope. Equally critical is the choice of propellants that feed these engines: liquid methane and liquid oxygen, collectively termed methalox. Most historical rockets burned highly refined kerosene, known as RP1, or liquid hydrogen. Kerosene is energy-dense and easy to store, but when burned in rocket engines, it deposits thick, gummy layers of black carbon soot inside the intricate plumbing and turbo machinery. This soot requires extensive, expensive disassembly and cleaning between flights, making rapid aircraft-like reuse nearly impossible. Liquid hydrogen, while offering the highest specific impulse of any chemical fuel, presents a logistical nightmare. Hydrogen molecules are so tiny that they leak through microscopic crystal boundaries in metal, boil off rapidly even under extreme insulation, and require gigantic, fragile fuel tanks due to hydrogen's extremely low liquid density. Methane hits the theoretical sweet spot. It burns clean with virtually zero soot buildup, enabling immediate engine relighting without refurbishing. It is dense enough to allow compact steel tanks, and its boiling point of minus 161 degrees Celsius is very close to liquid oxygen's boiling point of minus 183 degrees Celsius, simplifying thermal management. Most importantly, methane can be synthesized directly on Mars using local resources. The epic journey to Mars begins on Earth at the launch pad, surrounded by a colossal steel launch and integration tower known as Mechazilla. Fully stacked, the Super Heavy booster is fitted with 33 sea-level Raptor engines arranged in concentric rings, while the Starship upper stage mounted atop it carries 6 Raptors, 3 sea-level gimbaling engines for control and atmospheric flight, and 3 vacuum-optimized engines with enormous flared nozzles designed for peak efficiency in the airless void of space. When the countdown reaches 0, the launch mount unleashes over 7,500 metric tons of raw thrust, burning propellant at a staggering rate of 20 metric tons per second. The vehicle lifts off slowly, trembling with unfathomable acoustic energy, before accelerating rapidly as it punches through the thick lower atmosphere and arcs eastward over the ocean. After roughly 2.5 minutes of power descent, the booster has accelerated the entire stack to supersonic velocities high above the bulk of Earth's atmosphere. At this critical juncture, traditional rockets would perform a gentle separation where springs or small explosive bolts pushed the stages apart before the second stage engines ignite. Starship instead utilizes a technique known as hot staging. A heavily reinforced perforated steel interstage ring positioned between the booster and the ship allows Starship to ignite its 3 vacuum Raptor engines while still firmly attached to the Super Heavy booster. The searing exhaust gases of the spacecraft vent outward through the interstage openings, pushing the ship away from the booster with tremendous force while preventing any loss of forward momentum. This hot staging maneuver maximizes payload efficiency, ensuring that every ounce of thrust contributes directly to reaching orbital velocity. Once separated, the Super Heavy booster flips itself around using cold gas thrusters and 4 massive unshielded titanium grid fins located near its apex. The booster reignites a cluster of its central Raptor engines to perform a boost-back burn, cancelling out its forward trajectory and hurling itself on a precision ballistic arc back towards the launch site. As it plunges back into Earth's atmosphere, the grid fins battle against supersonic shockwaves to steer the 71-meter-tall steel cylinder with millimeter accuracy. In the final seconds before impact, the booster performs a landing burn to kill its remaining descent velocity. Instead of touching down on traditional heavy landing legs that add parasitic structural weight, the booster slides into place beside the launch tower, where 2 giant mechanical arms, affectionately dubbed chopsticks, catch the descending rocket right out of midair by specialized load-bearing pins on its hull. This eliminates landing gear entirely, protects the engines from ground debris, and allows the booster to be repositioned immediately onto the launch mount for inspection, refueling, and rapid reflight. Meanwhile, high above the atmosphere, Starship's 6 Raptor engines burn for approximately 6 minutes, pushing the massive spacecraft to orbital velocity of 27,000 kilometers per hour. Once Starship shuts down its engines and enters a stable low Earth orbit, an essential reality becomes immediately apparent. Its colossal propellant tanks, which held 1,200 tons of cryogenic liquid at liftoff, are now virtually empty. The ship has expended almost all of its fuel, simply climbing out of Earth's deep gravity well and achieving orbital velocity. In this state, Starship cannot reach the Moon, let alone journey to Mars. It is an empty steel hull stranded in Earth orbit. This is where the true linchpin of SpaceX's interplanetary architecture comes into play: in-space cryogenic propellant transfer. Without orbital refueling, Starship is impossible. To fully reload the Mars-bound ship, SpaceX will launch a series of specialized Starship tanker flights. Each tanker is structurally identical to the standard ship, but contains enlarged propellant tanks in place of a pressurized crew cabin and cargo bay. The tanker launches, achieves low Earth orbit, and performs a series of orbital rendezvous maneuvers to match trajectories with the waiting crewed Starship. The two spacecraft meet in the silent vacuum of space, aligning their tail ends and docking firmly using high-precision quick disconnect umbilicals located near their engine skirts. Transferring cryogenic liquids in microgravity is one of the most challenging problems in modern aerospace engineering. Without gravity, liquids do not settle neatly at the bottom of a tank. Instead, surface tension causes them to cling to the tank walls, floating as chaotic blobs mixed with vapor bubbles. If a pump ingests these gas bubbles, cavitation can destroy the machinery in seconds. To solve this, Starship uses small reaction control thrusters to provide a gentle, continuous forward acceleration, creating a slight artificial gravity gradient known as ullage settling. This forces the liquid methane and liquid oxygen to pool firmly against the tank sumps, allowing specialized high-flow pumps to transfer hundreds of tons of dense cryogenic liquid from the tanker into the interplanetary ship. Depending on the specific payload mass and orbital trajectory, between 4 and 8 tanker flights will rendezvous with the Mars-bound Starship over the course of several weeks. The tankers feature advanced multi-layer vacuum insulation and active refrigeration systems to prevent cryogenic boil-off caused by direct solar radiation in space. Once the final tanker disconnects and deorbits to return to Earth, the Mars-bound Starship is fully loaded. 1,200 metric tons of subcooled liquid methane and oxygen sloshing inside its pressurized steel tanks, ready to power a heavy crew cabin and over 100 tons of scientific hardware across the solar system. The departure from Earth is governed strictly by celestial mechanics. Earth and Mars travel around the Sun at different speeds and orbital distances. Earth, orbiting closer to the Sun, moves faster than Mars. Once every 26 months, the two planets align in their respective orbits in a geometric configuration that allows for an energy-efficient transfer trajectory known as a Hohmann transfer orbit. Attempting to fly to Mars outside this narrow planetary window would require impossibly high amounts of energy and fuel. When the launch window opens, the Mars-bound Starship positions itself over Earth's night side and ignites its 3 vacuum-optimized Raptor engines for a massive trans-Mars injection burn lasting several minutes. The engines roar with nearly 1.5 million pounds of thrust, accelerating the ship past Earth's escape velocity of 11 kilometers per second, hurling the crew outward into a wide, elliptical, heliocentric orbit that will intersect the path of Mars 6 to 9 months later. Once the trans-Mars injection burn is complete and the engines fall silent, the crew enters the longest and most psychologically taxing phase of the mission, the interplanetary cruise. For the next half year, the spacecraft is an isolated, self-contained metallic island drifting through the freezing vacuum of interplanetary space. Unlike the cramped, claustrophobic Apollo command modules or the tiny cabins of modern orbital capsules, Starship offers an enormous pressurized volume of approximately 1,000 cubic meters, comparable to the total interior living space of the entire International Space Station. Inside this cavernous steel hull, engineers can construct multi-level decks featuring private sleeping quarters for each crew member, communal galleys, science laboratories, medical stations, workshops, and recreational areas designed to maintain physical fitness and mental health during the long voyage. Surviving the cruise requires overcoming severe environmental threats, chief among them being cosmic radiation. Beyond the protective embrace of Earth's magnetosphere and atmosphere, astronauts are exposed to 2 distinct forms of deadly ionizing radiation: solar particle events and galactic cosmic rays. Solar particle events consist of sporadic, highly energetic streams of protons ejected during coronal mass ejections and solar flares from the Sun. While potentially lethal within hours if an astronaut is unshielded, solar protons can be effectively stopped by materials rich in hydrogen, such as polyethylene, food rations, and water. Starship leverages this physical reality by arranging its primary life support water storage tanks, grey water recycling reservoirs, and densely packed cargo containers around a central storm shelter within the core of the ship. When onboard sensors detect an incoming solar storm, the crew retreats inside this heavily shielded central bunker until the radiation flux subsides. Galactic cosmic rays, however, present a far more insidious and persistent threat. Emanating from exploding supernovae and energetic astrophysical phenomena outside our galaxy, these particles consist of heavy atomic nuclei stripped of their electrons, traveling at nearly the speed of light. Because they possess extraordinary kinetic energy, they slice directly through rocket hulls, shattering atomic nuclei in the metal and producing dangerous showers of secondary radiation. Heavy physical shielding against cosmic rays is impractical due to weight limits. Therefore, the primary strategy to protect human biology against cosmic rays is speed. By utilizing powerful Raptor burns and high-energy transfer trajectories, Starship minimizes the total transit time to roughly 6 months, thereby keeping the crew's cumulative lifetime radiation dosage well within acceptable occupational safety margins established by global space agencies. Simultaneously, the crew must battle the silent physical degradation caused by prolonged microgravity. In the absence of gravitational loading, the human body adapts rapidly to weightlessness by shedding bone mineral density at a rate of 1% per month, allowing skeletal muscles to atrophy and cardiovascular systems to weaken. Fluid shifts towards the head can also increase intracranial pressure, leading to visual impairment and optic nerve swelling, a condition known as spaceflight-associated neuroocular syndrome. To combat these debilitating physical declines, the crew must adhere to a mandatory, rigorous daily regimen of 2 or more hours of intense resistance training and cardiovascular exercise using specialized bungee-loaded treadmills, stationary bicycles, and advanced resistive exercise devices bolted into the ship's structural bulkheads. Keeping dozens of humans alive for months without resupply also demands nearly perfect closed-loop environmental control and life support systems. Starship's life support architecture recovers and purifies virtually every drop of moisture expelled by the crew. Sweat, exhalations, and urine are captured through condensing heat exchangers, multi-stage filtration membranes, catalytic oxidizers, and vacuum distillation units, recycling water with an efficiency exceeding 98%. The carbon dioxide exhaled by the astronauts is continuously scrubbed from the cabin atmosphere using regenerative solid amine beds. Instead of venting this carbon dioxide into space as waste, it is fed into an onboard Sabatier chemical reactor, where it is reacted with hydrogen gas generated from water electrolysis to produce clean water and methane. Oxygen is continuously regenerated by splitting purified water molecules using electric currents generated by the ship's deployable solar arrays. As the months tick away, the reddish glow outside the forward observation windows grows from a faint beacon into a massive, rust-colored sphere scarred by ancient impact craters and colossal geological chasms. The crew conducts intensive system checks, secures all loose equipment, straps into their custom-molded acceleration couches, and prepares for the most violent, hair-raising phase of the entire mission: Mars atmospheric entry and landing. Arriving at Mars after an interplanetary transfer, Starship approaches the planet at an astonishing velocity of approximately 7.5 kilometers per second, or 27,000 kilometers per hour. To land safely, the spacecraft must dissipate that monstrous mountain of kinetic energy without running out of fuel or burning up in the process. The atmosphere of Mars presents a notoriously treacherous challenge to planetary scientists. It consists of 95% carbon dioxide, but its surface atmospheric pressure is less than 1% of Earth's. This creates an awkward aerodynamic regime. The air is far too thin to slow down a massive 100-ton spacecraft using parachutes, yet it is thick enough to generate intense shockwaves and plasma temperatures exceeding 2,000 degrees Celsius during high-speed entry. Starship conquers this dilemma through an audacious maneuver known as aerodynamic aerocapture and the belly-flop skydiver descent. Rather than entering the atmosphere nose-first like a traditional capsule or using huge amounts of rocket propellant to break into orbit, Starship plunges directly into the upper Martian atmosphere at an extreme 60-degree angle of attack, belly first. The entire windward side of the spacecraft is coated with thousands of hexagonal ceramic thermal protection tiles. As the flat underbelly of the ship slams into the thin Martian atmosphere, it creates a detached bull shockwave that absorbs the brunt of the blistering atmospheric friction, dissipating over 99% of the vehicle's interplanetary kinetic energy entirely through aerodynamic drag without burning a single drop of fuel. Throughout the hypersonic, supersonic, and subsonic phases of the descent, Starship does not fly like an airplane with aerodynamic lift. Instead, it falls like a human skydiver. 4 large, independently actuated body flaps, 2 forward and 2 aft, powered by powerful electric motors, continuously adjust their angles to control pitch, roll, and yaw. By deflecting the flaps against the rushing airflow, the ship's autonomous flight computers maintain perfect stability through the turbulent Martian atmosphere, bleeding off speed until the vessel is falling through the lower atmosphere at a terminal velocity of roughly 250 kilometers per hour. At approximately 1 kilometer above the rocky Martian surface, Starship performs a jaw-dropping transition known as the landing flip maneuver. With the ground rushing up at terrifying speed, the flight computers ignite 3 central sea-level Raptor engines and gimbal them violently to the side. The massive thrust overcomes the aerodynamic forces, swinging the 70-meter tall ship from a horizontal belly-down orientation to a perfectly vertical landing attitude in a matter of seconds. The engines throttle down rapidly, compensating for Mars's lower gravity, which is only 38% of Earth's. As the Raptor plumes kick up massive clouds of red dust and basaltic sand, Starship extends its rugged steel landing legs and touches down softly on the ancient Martian plains. After a journey of hundreds of millions of kilometers, humans have officially set foot on another world. Touching down safely on Mars is an extraordinary achievement, but it is only the halfway mark of the mission. The spacecraft is now stationary on a frozen, airless, irradiated desert where the average surface temperature hovers around -60 degrees Celsius. Atmospheric pressure is practically a vacuum, and no breathable air exists. In the initial phase of surface operations, Starship itself serves as the expedition's primary habitat, power station, and laboratory. The crew does not immediately construct sprawling brick-and-mortar domes. Instead, they live and work within the pressurized, climate-controlled decks of the spacecraft, descending to the Martian surface via external mechanical cargo elevators mounted to the hull. The first critical task on the surface is deploying a massive, reliable power generation infrastructure. Chemical fuel cells and batteries are inadequate for long-term planetary operations. The crew will deploy large arrays of ultra-thin, flexible photovoltaic solar panels across hundreds of square meters of the surrounding terrain, supplemented by compact nuclear fission surface power units such as NASA-designed kilopower reactors. Nuclear power is essential on Mars because seasonal dust storms can engulf the entire planet for months at a time, blotting out the sun and reducing solar energy production to near zero. Constant megawatt-scale electrical power is the lifeblood of the entire Martian base. This massive electrical output is required for the most crucial industrial operation of the mission, in-situ resource utilization, or ISRU. Remember the fundamental rule of the rocket equation. Starship cannot carry the fuel required to return to Earth with it from the start. To fly home, it must manufacture hundreds of tons of liquid methane and liquid oxygen directly on the surface of Mars from the native resources of the planet. The chemical factory that makes this possible relies on two straightforward, proven chemical reactions: water electrolysis and the Sabatier methanation reaction, first discovered by French chemist Paul Sabatier in 1912 AD. The raw materials needed for these reactions are abundant across Mars. The Martian atmosphere provides a virtually limitless reservoir of carbon dioxide gas, while billions of tons of water ice lie locked beneath the regolith as buried glacial sheets, particularly in mid-latitude regions such as Arcadia Planitia. The resource harvesting process begins with automated robotic rovers and excavation machinery scraping away the top layer of dry dust to mine the subsurface water ice. The excavated icy regolith is transported into specialized sealed sublimation ovens, where waste heat or electrical heaters vaporize the ice into steam, leaving behind barren gravel and toxic perchlorate salts. The purified steam is condensed into clean liquid water. Next, this purified water is fed into an array of industrial electrolysis units powered by the surface nuclear reactors and solar fields. The electrical current splits the water molecules into hydrogen gas and oxygen gas. The oxygen is scrubbed, compressed, and fed into heavy-duty cryogenic liquefaction chillers, where it is cooled to minus 183 degrees Celsius and stored as liquid oxygen in the ship's main oxidizer tanks. The byproduct hydrogen gas is then combined with carbon dioxide drawn directly from the Martian atmosphere. Compressors pull in the thin Martian air, filter out atmospheric dust, and pump the carbon dioxide alongside the hydrogen into a high-temperature catalytic Sabatier reactor filled with nickel or ruthenium catalysts. Under temperatures of 400 degrees Celsius, the carbon dioxide and hydrogen react spontaneously to produce methane gas and water vapor. The resulting water vapor is condensed, separated, and cycled straight back into the electrolysis units to be split again, while the methane gas is purified, compressed, and chilled down to minus 161 degrees Celsius, transforming into crystal-clear liquid methane. Producing the full propellant load of 1,200 metric tons requires roughly 2 full Earth years of continuous chemical refining on the Martian surface. This timeline aligns perfectly with orbital mechanics. Because Earth and Mars only align every 26 months, the crew must remain on the surface for approximately 500 to 600 days before the celestial return window opens. During this extended stay, the astronauts conduct extensive scientific research, exploring ancient river valleys, searching deep subterranean lava tubes for potential biosignatures of past microbial life, and assembling the foundational infrastructure for future expeditions. When the two planets once again swing into optimal alignment and Starship's massive steel tanks are filled to the brim with Martian-made cryogenic propellant, The crew prepares for the journey home. The departure from Mars is remarkably simpler than the initial launch from Earth. Because Mars is a smaller planet with only 38% of Earth's surface gravity and has virtually no thick atmospheric resistance, the Starship upper stage does not require a giant super heavy booster to reach orbit. Starship is fully capable of launching directly from the Martian surface as a single-stage-to-orbit vehicle. The 6 Raptor engines ignite against the Martian soil, lifting the steel ship smoothly into the salmon-colored sky. Starship ascends through the wispy carbon dioxide atmosphere, achieves Martian orbit, and conducts a precision trans-Earth injection burn. The engines fire for several minutes, flinging the spacecraft out of Martian gravity and locking it onto an elliptical trajectory back toward the blue and white marble of Earth. After another 6-month interplanetary transit, the crew arrives back at Earth at extreme hyperbolic speeds exceeding 11 kilometers per second. Once again, Starship turns its heat shield-covered belly to the oncoming atmosphere, slicing into the upper reaches of Earth's air to bleed off its interplanetary momentum in a fiery display of hypersonic physics. The ship survives the searing plasma sheath, performs the skydiver flap glide, executes the final Raptor landing flip near the launch site, and descends into the waiting arms of the launch tower chopsticks or lands gently on a coastal pad. The full cycle of human interplanetary flight is complete. The true significance of SpaceX's Starship architecture lies not in a single heroic journey, but in its scalability. Starship is not designed as an isolated Apollo-style flag-planting machine. It is designed as a heavy freight railroad to the cosmos. By mastering full reusability, orbital propellant transfer, and in-situ fuel synthesis, the cost of sending mass to the red planet drops by several orders of magnitude. What begins as a single exploratory voyage with an intrepid crew of scientists and engineers transforms over subsequent launch windows into a coordinated armada of dozens, then hundreds of ships departing Earth in fleets every 2 years. Cargo ships packed with autonomous heavy machinery, solar farms, 3D printing construction robots, life support modules, agricultural greenhouses, and nuclear generators will pave the way for permanent human settlements. Over successive decades, early base camps will expand into modular research outposts, subterranean lava tube habitats shielded from radiation, and eventually the bustling streets of humanity's first self-sustaining interplanetary city. By transforming the hostile void between Earth and Mars into a routine, navigable highway, Starship does more than solve a formidable engineering puzzle. It ensures the long-term survival of human consciousness, expanding life beyond its single planetary cradle and marking the dawn of our era as a truly multi-planetary species.